We'll now discuss exactly what it means for a function to be continuous. So we start with it being continuous at a certain point. We say a function is continuous at a certain point x0 if the limit as x approaches x0 of f of x is equal to f of x0. So essentially we want the limit to be equal to the function value, and that tells us that a function is continuous. And we say that an entire function is continuous if it's continuous at every single point in your interval. So now that we have some idea of continuity, let's look at some continuous functions that we know. So first, power functions are continuous. So anytime we have x to a power, that is going to be a continuous function. Polynomials are also continuous functions. And trig functions are also continuous. There is some ambiguity there with things like tangent because it's not defined at pi over 2. But if we just restrict our interval to not include those endpoints, then it will be a continuous function. Exponential functions are also continuous, and so are logarithms. And there's a lot more functions that are continuous. These are just a few examples. So now let's look at a particular example and see if we can figure out when it's continuous. So here, I want to know when f of g is continuous. I know that f of x is x squared plus 2 and g of x is ln of x. So if I try to find f of g, I have f of ln of x, which is ln of x squared plus 2. And so it's important to note here that this is going to be continuous over the interval 0 to infinity. And that's important because the natural log is not defined on any negative numbers or on 0, which is why we have to include only the positive numbers. And compositions are going to be very interesting that way. Essentially, that last example, if we go back to it, we know that polynomials can be defined anywhere, and ln of x was only continuous at 0 to infinity, so it made sense that the composition was continuous at the smaller of those two intervals. So how does composition affect things like limits? So let's suppose we have this let's suppose that we know the limit as x approaches x0 of g of x is L, so we know this exists, and we know that f is continuous at that point L. Then in that case, we know that the limit as x approaches x0 of f of g of x is the same thing as the limit of, is the same thing as f of the limit as x approaches x0 of g of x, which is f of L. Essentially, what this is telling me is that I can actually move a limit inside and outside of a composition of functions. So let's do some examples to show how this works. I want to find the limit as x approaches 0 of ln of sine x over x. What this says is I can start by just taking the limit as x approaches 0 of sine of x over x, which we've talked about in a previous video, and we said that that was 1. So this is just ln of 1, which is 0. Didn't quite work. So let's look at another example. Here I have the limit as x approaches 1 of sine of x squared plus 8x minus 8, all divided by x minus 1 plus 6 over pi. And this looks super confusing, but remember, we can just stick in 1 for x in order to take that limit. So on the top, I have 1 plus 8 minus 8, which is 1. And on the bottom, 1 minus 1 plus 6 over pi, which is just 6 over pi. When we're dividing fractions, we flip the denominator and multiply, so we end up with just sine of 6 pi. And when we try to take that sine of pi over 6, we just get 1/2. So we have our limit.